Fusion Mobile, quality e-learning experience on the go.
My dear, today we'll be treating fluids at rest and also fluids in motion. There are three major parameters we'll discuss here. The first is the surface tension, the second is the capillarity, and the third is viscosity. Talking about surface tension, the tension or force acting parallel to the surface of a liquid is what we mean by surface tension. When the surface of a liquid behaves as if it were covered by an elastic skin, just like a nylon, the surface thus appears to be under some force or tension, and this tension is known as surface tension. For example, when you drop your cork on top of a bucket of water filled with water, you'll notice that the cork will stay on top of the water as if it's bouncing. It cannot go in because of what? Surface tension. Applications of surface tension. 1. Waterproof materials used for umbrellas, raincoats, or tents are usually treated with oil-based substance which prevents water from wetting the materials. Your umbrella is made with cloth, but can you come out on the daylight and use your cloth as an umbrella? No. But when we coat them with an oil surface such that water can no longer go in, we'll say that we have created an effect of surface tension and is applicable to importance to man. Cleaning action of soaps and detergents is also an application. Now, in surface tension or in liquids, we have two kinds of force. We have the adhesion and the cohesion. The force of attraction between molecules of the same substance is called cohesion, while the force of attraction between molecules of different substances is called adhesion. Both are force of attraction, but in cohesion, the attraction is between molecules of same substance, while in adhesion, the attraction is between molecules of different substance. Example, when you pour water into glass, the water wets the glass. That is force of what? Adhesion. But mercury has high strong cohesion. So when you pour it in a glass, it cannot wet that glass. We'll bring it to capillarity. We all take our drinks with straw. And they do a little experiment for me. When you drop your straw inside the drink, you notice that there is a climb of the fluid through the straw above the surface of the straw, above the surface of the drink liquid you are taking. This is as a result of capillarity. It is defined as the tendency of liquids to rise or fall in a narrow capillary tubes. When you use your straw to do that, you notice the rise we are talking about. And when the volume is enlarged, let's assume the bottle becomes bigger, it falls. So the tendency of the liquid to rise or fall in a narrow capillary tube is what we call capillarity. Talking about surface tension mathematically, it is given as T, which is the surface tension, equal to force on the fluid divided by length on that fluid. This is the formula for surface tension. It's not rampant in our textbooks, while the coefficient of surface tension is given as T equal to R H rho G all over 2. And you know, rho GH is giving us, from here, is giving us pressure. So this simply means that tension here, T, is the radius of the particular capillary we are talking about times pressure divided by 2. But this formula, I want you to take a critical look at it and derive it from how we got it. For further reading, you can consult my test, Divine Touch, Volume 1. We now come to viscosity. In viscosity, we said that is the friction between two layers of a fluid. It can happen in oil, it can happen in water, but we notice that the denser the fluid, the higher the viscosity. And in viscosity, we discuss what we call the terminal velocity. Mathematically, viscosity can be arranged with this relationship mg, which is weight of the body, minus velocity minus upthrust, which is equal to the total force of the system, mass times acceleration. Now, if this is true, when there exists no force in the system, no net force, that means mass times acceleration is equal to 0. We have mg minus v minus u to be equal to 0. Making v the subject of the formula, we have it that v will be equal to mg minus u. This is known as terminal speed. If I'm representing it in a graph, we'll have something this way, where here is representing our velocity and this point is representing our time. If I'm plotting it in a graph, at this point we still have acceleration, and when it gets to a point here, it will come this way. That means at this point is known as our terminal velocity, while at this point we still have acceleration moving. I hope you enjoyed that short topic, but you really need it to take further understanding later when we'll be discussing about fluid again, when we'll start talking about Archimedes' principle and the rest of them. From there, we'll come to this topic, a very wonderful one, the baseline of physics, known as vectors. Meet you in that class. Thank you.